Okay, welcome everyone to our next lecture. Today we will talk about matrix differential calculus, but before we do that, I want to go back to the older lecture, section 7, where there was a big hole in the lecture, which I filled up in the video already. Just want to let you know that it is filled up now. So what was it about? It was a transformation example, quite curious. And it was something about starting with a certain density, deriving another density using some nonlinear monotonic transformation. And then there was a hole. Basically, the hole was, I was claiming that there's a certain expectation being equal to logarithm of a divided by b. And I'm saying that till 2011 or something. And I forgot when I checked that. So I checked it last time, and I couldn't figure it out. That's what the hole was, and it's wrong, okay? What's surprising? How surprising is that? So the expectation is not equal to the logarithm, which looked weird anyway. It looked like dragging the x nonlinear function inside the expectation, which you know, the math people know it. So with Jensen's inequality, you can do it for convex functions, but then you don't have equality but an inequality. So in general, the integration is only linear. So I thought there's something magic going on with the transformation of variables rules here, but it's not. It was just wrong. So it is not equal. So basically, when you nonlinearly transform a random variable, the mean can transform, okay? Let me also give you on the board a very simple example. Simple is always relative. No, maybe I don't give it on the board. So I give you an example basically inside a Jupyter notebook. So I implemented these things. So here's a sample from a beta distribution in Python. And now I'm having these transformations exactly as on the slides. And then I can calculate the means, and they do not agree. Okay, so this is a counterexample to what I always said in the lecture. However, of course, I was curious to calculate this stupid mean after the transformation. And actually it is possible, yeah. It's always possible when you find the right answer somewhere online. So on some Stack Exchange page, from the statistics Stack Exchange one, they were explaining how to calculate the PDF of a logarithm, okay? And if x is beta distributed, exactly what we need, kind of, right? We can combine it then with having a quotient. And it turns out that the expectation of logarithm of pi, where pi is now a random variable, beta distributed, is this psi of a minus psi of a plus b, where psi is the so-called di-gamma function. And di-gamma function means, I think I have it on the slide somewhere, also something that you don't need to memorize. So the di-gamma function, do I have it here? No, I don't have it here. Oh, there it is. The di-gamma function is the derivative of the logarithm of the gamma function. Okay, so yet another weird function that got the fancy name. Okay, and we can just use it. Perfect. So, and of course, there is an implementation of all these weird functions in these toolboxes. So there's also a di-gamma implementation. Where did I find it? It's typically in SciPy Special, where also the beta function is and some other weird functions. And the di-gamma function is there as well. So, and if we do some more tricks, a little bit of tricks here to do the right calculation, it turns out that our empirical estimate is approximately the same as the estimate that comes from our formula, which is nice. So now we have a formula, and we also have the true answer, which is good. I also put it all on the slide here. So basically, one starts that the expectation of logarithm of pi is this difference, and then when you have a quotient like that, you can use these tricks of the integration and of logarithm, and then you can derive the answer. You don't have to be able to do that. It took a half afternoon for myself, and I also told the PhD students, hey, look at this might be wrong or true, can we prove it? And then one of them also was calculating and couldn't do it, and at the end we had the solution together, which is great. Anyway, so now what do we learn? So the mean changes also under a nonlinear transformation, okay, too bad. As does the mode, so the maximum as well. However, the median is fine, so the median does not change. So why is that? The median is that location where 50% of the mass is on one side and 50% of the mass of your PDF is on the other side. Now, if you have a monotonic transformation of your density, basically you are not changing the ordering of the different locations. You are just changing kind of the weight that they receive. Okay, so also after any monotonic transformation, 50% of your friends are on one side and 50% of your friends are on the other side. So the median stays the same. Of course, this is a hand-wavy proof, but you can make it more precise by writing it out that the integration on one side should be the same as the integration on the other side, and so on and so forth. Okay, so what does it tell us? So you have to be careful with your parameterization. The parameterization influences your estimation, okay? At least if you are not fully Bayesian and take the posterior. When you take the posterior, things are nicer and things could be better. However, I'm not going into the details, not to introduce another wrong statement here. Yeah, but that's basically the story. Good, so it's always nice if at the end we can calculate something. So far, so good. Today we will talk about the matrix differential calculus. You might wonder why. So, okay, we understood he's a mathematician, kind of, but actually I'm a computer scientist by heart. But I figured out that mathematics is basically computer science. It's the same thing. They're just using, instead of a programming language, they're using pencil and paper. It's the same thing. But they're also trying to be very precise. The compiler is typically another person that reads the proof, for example, if you do mathematics. And so they are very related, the fields. So now why do we need matrix differential calculus? We need it, for example, in linear regression to derive these formulas here. Yeah, to minimize the log likelihood for a Gaussian distribution, in order to derive this formula, we need some way to calculate derivatives. However, typically in school, you only learn to calculate derivatives for scalar functions that have a scalar value at the end, so a scalar input and a scalar output. Maybe in analysis 2, you also learn how to calculate the gradient or some Jacobian matrix, these kind of things, but typically you do it with your scalar formulas, with your scalar tricks. Okay, so you have a calculus for deriving scalar derivatives. That's what we are typically taught. However, there's also calculus to do this all vectorized or even on the level of matrices. And I think this is very powerful and very fancy to do. And at the end, I show you an example. I show you a couple of examples which are quite difficult to do by hand, right? For example, calculating the derivative of a determinant or calculating the derivative of eigenvalues or something like that. That's really tough. And maybe at some point you want to do that. Yeah? Maybe not. But if you want to do something like that, you need some mechanism to do it, okay? You can hope that the implementers of the PyTorch toolbox are implementing all the layers for you already. However, for a long time there was no Fourier transform in the PyTorch library, and so you had to do it yourself. So you had to figure out, if I have a Fourier transform as a transformation in a layer, what is the derivative, okay? And once you implement that, you can put the layer into the toolbox and use it and combine it with everything else. And then maybe there's another transformation that's not in there yet, the radon transform or whatever, and you want to use it in a neural network, so you need the derivative of that. And that you need to calculate by hand typically, right? If you do the standard stuff that everyone else is doing, you don't need it. Good, so linear regression summary. There were certain model assumptions, and I've tried to write them down very uniformly so that we can derive different methods from it, okay? Having a Bayesian head-on, we also claim there is a prior on our parameter. Of course, if you do classical statistics, you never would formulate it like that. At the end, you would say, yeah, this is the solution. However, X transpose X is sometimes very badly behaved. Or with other words, some eigenvalues might be really small, so you don't want to invert that matrix. So we add something on the diagonal. However, if we write it down like this with the prior on W, we can also derive this regularization just by doing Bayesian inference, which is quite nice, because it gives us an interpretation of what we are really doing, okay? Actually, there's a whole field called probabilistic numerics, where I think, among others, Philipp Hennig, with whom I gave these lectures a couple of years ago as well, he's one of the main proponents in this area. Probabilistic numerics is exactly about that. You write down a probabilistic model, and you derive an interesting algorithm using Bayes' rule, okay? And then you wonder, so to what algorithm does it compare? And actually it turns out many methods in numerics, like quasi-Newton methods and these kind of, they could be derived using a probabilistic derivation where you have certain assumptions, okay? Why is it interesting? Because it shows you now that a certain quasi-Newton method that is approximating the Hessian in a fancy way can be understood like a Bayesian estimation procedure. And that means now if I change my assumptions in my Bayesian estimation procedures and maybe go from a Gaussian distribution here to a more complicated Gaussian distribution or to some other distribution, I get a completely new numerical method, right, which hasn't been known before. So by understanding the principles and assumptions of these numerical methods, that allows us kind of also to extend the toolbox of numerics people. And it also applies to many other fields. I think recently there is also a Wikipedia entry for probabilistic numerics, so please look it up. It's a really interesting topic, which connects machine learning and numerics in an interesting way. Good, so we had these different solutions here. And we could also do Bayesian linear regression, where basically we also get additionally now also the covariance matrix. So basically the answer here of Bayesian linear regression is not Wn is equal to this expression, but the answer is a Gaussian distribution with a certain mean and a certain covariance matrix. So that is the answer. And then you could go on for predictive posterior distributions or these kind of stuff to go on with it. So now I hope now you also want to be able to derive this thing. I think there's also a question on it on the next exercise sheet. So you should be able to do it after this lecture, hopefully. So how can we calculate derivatives of scalar or vector or matrix valued function? So the first thing refers to the output, okay, of scalar, vector, or matrix valued variables. So that refers to the input. Okay, so for all combinations we want to do it. Actually, at the end, to be honest, typically we look at scalar valued functions, right? Why? Because we are interested in loss functions. You want to minimize a scalar number. You want to minimize a single number typically, a single number which is the loss of a mismatch in a classification problem or in a regression problem. However, your inputs, your parameters, they can be high dimensional. So they could be vectors or matrices or more complicated things. And it turns out that for this case, it's particularly easy often. Good. So it is somewhat quite involved, powerful method to get super complicated derivatives where we have vectors and matrices. So there's certain material which I could point to. So there's one which is called BN142. That's like my cheat sheet that I created once with some worked out examples. If you find typos, please tell me. So that is the PDF where all the formulas of the calculus are listed with some examples and instructions. Okay. Then there's a book from Magnus Neudecker. So those are, I think, econometricians who were also suffering from deriving some derivatives. And so they kind of, I'm not sure whether they really derived it, but they kind of worked out all the details of this matrix differential calculus in a nice book from 2007. And the PDF was available at this location here. So maybe you can go to this location and look for the 4th edition, whether it's also available. Or maybe from the file name you find some other copy from someone still of the old version, if it's still out there somewhere, I don't know. However, it's not officially distributed as a PDF anymore. However, much of this book can be also found in a certain paper which is still available. Okay, so this paper is also summarizing the method in great detail. And here's another one. So this is also a PDF where you have lots of the material. Then there's another really nice book, the so-called Handbook of Matrices from 1996 from Lütgepohl. I'm not sure whether it's available online. It's also a quite nice book where you can find everything about matrices, okay? Starting that A plus B is equal to B plus A, up to super sophisticated things about eigenvalues and eigenvectors. And it's just a list of results without any proofs. So you have a whole table for formulas and tricks that deal with the Kronecker product of two matrices, and then whole pages that deal with the Hadamard product of matrices and all these things. And maybe you thought that this is not useful at all. However, when you do these calculations, sometimes you're getting weird expressions where you get stuck, and then you need the handbook of matrices to find out the right trick. However, the tricks that I usually use, I will show you all in the lecture, and they are like all written down on the slide. So that's already like a nice formula collection here on these slides or in these papers as well. So differential, first of all, what is the differential, right? And didn't we want derivatives? I mean, why are we talking about differentials? So the trick here is, it's easier to derive here differentials for complicated formulas. And once you have the differential, you can read off the derivative. So that is the basic idea. You derive the differential instead of deriving the derivative, and then you can read off the derivative, okay? So that's the idea. So the short answer to what is the differential, the short answer is the differential is exactly this dx in an integration, okay? So that is the differential, which is typically more written like a notation, but it has a name and it has some meaning and some theory. Also, if you write a derivative like dy divided by dx, then you're also using two differentials, okay? However, we can also define it as follows. So a differential is an infinitesimal change, so a super small change, an arbitrarily small change in some varying quantity, okay? For example, if x is a variable, its differential is denoted as dx. And note, I haven't told you what type this is. So this could be a scalar, a vector, or a matrix, yeah? In general, we would put a little d in front of it, and then we get an object that has exactly the same shape. So if x was a vector of length 10, then the dx will be also a vector of length 10, which makes sense, right? When you write down the formula for the derivative, sometimes you write it in a way that you say the function value at x plus dx, okay? And then you say the dx is a small number, but in principle, if x is a vector, the dx might be a small vector, okay? So you must be able to sum those two things up. Suppose you have a variable that is defined as the image of x under some function f, then the differential is interestingly dy is equal to the derivative of x, okay, of f with respect to x times the differential of x, okay? So that is basically, yeah, the definition now is more a hand-wavy definition here, right? But let's see what we can make out of this. So suppose we use the Leibniz notation for our derivative, which is dy divided by dx. Then it turns out that it comes something very reasonable out of this, right? So dy is equal to dy divided by dx times dx. So it kind of makes sense. But again, you know, I'm a bit hand-wavy here. Look at the real math books for the details, right? But this is the intuition, okay? So the differential is about the small change, and the derivative is about the ratio of the small change in y divided by the small change in x, just as we define the derivative. So the differential is exactly the thing in the definition of a derivative that you put on the top of the bar or at the bottom of the bar, okay? That's exactly the differential. Now an integral, for example, can be also just viewed as the summation over infinitesimally small rectangles, like in the Riemann integration, right? So this is an equal, it's not really an equal sign, so this should be an approx, okay? However, if this is, again, non-standard analysis, if the dx is really super, super small, then this is equal in a way, okay? So this dx has really a meaning in integration, okay? It is really length on the x-axis times the height. Length on the x-axis times the height, just like in Riemann integration where you sum up these columns. That's exactly the same thing. Good. So now what about the derivative? For the derivative now here in the context of matrix differential calculus, I'm using this notation. I'm writing a capital D in front of the function f of x. Okay? It's curious how you would put the brackets here. The brackets are actually around the capital D and the little f. So the capital D is the derivative operator that has as an input a function f, and it can be evaluated at location x. Okay, so it's not about f of x, and then you have the derivative of that one, but it's actually the D is an operator on the function. It gives you another function, and you can evaluate it at location x. Or if you like this notation, it's the same as that one. Okay, good, so far so good. Now here comes like the first identification formula just derived from the definition, okay? So if I have an expression for my differential for my function f, okay, that can be written in such a way that the dx is isolated on the very far right-hand side, the expression in front of it is the derivative, and I can read it off from the expression, okay? Now what about that one? this is similar to our way we wrote y of x, right? Where I also said the value y is little letter y, but little letter y can be also seen as a function of x. Okay, so here, now I don't mean the function f, but here I'm also meaning a particular value. So maybe my notation is not super consistent here. So now, how can we calculate a derivative with differential calculus? So here is the algorithm. Okay, this is your recipe. You write the letter d in front of your expression, okay, since you want to have the differential of the complicated expression, like above, you want to have the differential of f, so you write the letter d in front of the f. Then you need to make sure which expressions in your complicated term are constant and which are variable, okay? Then you use the calculus, which I show you on the next slides, so basically some rules to transform the expression in such a way such that the dx is on the very right-hand side. And then you can just read off the derivative. Okay, so that is the recipe for the matrix differential calculus. Okay, so notation is super important here. Yeah? So the notation in the rest of the slides, and actually I try to do it often I try to use this notation when I do derivations on my sheet of paper. I use small Greek letters for scalars, I use small Latin letters for vectors, and they are typically always column vectors for me, okay? And I use capital Latin letters for matrices. Okay, that's super nice because then you always know the type of everything and you can quickly check whether everything is okay. Okay? So that is the notation, very important. Here comes the first rules of our calculus. So suppose we only have scalars, yeah? That's why there are all these Greek letters here. And let's assume the alpha is constant, yeah, and some other variable is the one where we are interested in, which might not appear here on the slide even, okay? But we know the alpha is constant. Then first of all, the differential of alpha is equal to 0, okay? So that's the first thing. It's like saying the derivative of the constant function is equal to 0, right? So suppose alpha, you would view it as a function of some xi, of some other scalar input, but it's constant. Yeah, it doesn't change with xi. Yeah, let me write it maybe on the board. It's easy, but one should be aware of it. So suppose this alpha of xi is constant. So I'm interested in this function here, yeah? Then I would say I put the d in front of the alpha. I could have put in here also the xi, right? But that doesn't matter. I've tried to be super economic with the stuff that I'm writing down. So I'm just saying d alpha. So what is the change in alpha if I fiddle around with the xi? Okay, so basically from my calculus it's 0, and let's write it a bit more complicated. That's the same as 0 times d xi. Okay, and now I can read off my derivative here. Okay, so it kind of all makes sense. So it describes a little change in my input variable. How does it influence the output variable? Okay, and for a constant, it's not influencing it at all since it's constant, so the derivative is 0. So next one, if you have an expression alpha times phi, yeah, then you can drag out the alpha. And that's the same like if you have the derivative where you can also drag out a constant. Okay, that's like the same formulas as those ones. For the phi, we don't know. So that could be a more complicated expression, for possibly one with matrices where you calculate the trace of the matrix or something. The key is the type of phi will be a scalar. So the size of it is 1 by 1, okay? And we should now go on with the d phi here in this and put in the expression for the phi and go on and on and on and then collect all the expressions. Next one. This is the sum rule, and it is just the sum rule. So you see here the differential behaves very much like all the rules that you already know. Question? Oh, I didn't change. Okay. Thank you very, very much. So that improves the video a lot when you tell me that. So this is just a summation rule, okay, as you know it. This is just a product rule as you know it. And this is just a quotient rule as you know it. So everything is just fine, okay? Nothing surprising happens. So I show you an example. So let's find the derivative of phi of xi, but let's use now the matrix differential calculus. So in Up to now, by the way, it's a scalar differential calculus. So since there are no matrices yet, do I have some spoon? Okay, so let's try it. So our expression got a name. So we say phi of xi is equal to xi squared. Fine. So how do I do it? I put the letter d in front of my expression I'm interested in. So I put a d in front of the phi. So far, so good. Now for the phi, I have an expression. I have xi squared, right? So now I'm really working more like a, think more like compilers or like really like term replacement system. I'm really doing just term replacement here. So I'm just replacing the phi with the xi squared. So let's write that one out. So that looks a bit complicated with the squared, right? We don't know so much yet. Let's write it like this. Okay, great. That means now we can use the product rule here. Okay, so the bracketing is like that. So it's like differential of a product of two scalars. So that basically means I have to have the differential of the first one times the right-hand side plus the left-hand side times the right-hand side. Okay, now we know scalar multiplication is commutative. Okay, so we can flip it around, which means now we get 2 times xi times d xi. And at this point we are done. Yeah? Now we can read off the derivative of our phi at location xi, which is just this expression in front of the d xi. You might wonder, so does it always work? Can you always do this? Isolate the d xi? Maybe not. All the things I tried, it worked. Okay, but there might be derivatives which you just cannot calculate because it gets too complicated. However, all the things I tried so far, that is always possible kind of to isolate the dx, the d xi squared. So I'm not sure whether I did it also with that many details here. No, I did not. But so basically, that is the same calculation here. Okay. So it's a simple example, and of course here you would have used your typical rules that you use, and it's much easier. But when you use vectors, it gets a bit more complicated. Let's look at the rules for vectors. First of all, it looks like the only thing that changed is that we changed all Greek letters now with Latin letters, and the rest stayed the same. Okay, so a is now a constant vector, and alpha is a constant scalar. So the differential of the constant vector is 0. However, it's 0 sub n, right? Which means it's the vector of shape n times 1, where they are all in zeros in here. So basically that is another notation for numpy dot zeros, bracket open n, bracket close. Okay, so that is exactly the same thing. It's a mathematical way to write down the 0 vector. So if I have a scalar with a vector, I can also just drag it out. If I have a summation of 2 vectors, of course, they must have the same shape, right? Otherwise, I cannot sum them up. Yeah? Then it's just a summation of the differentials. And if I have a product, now this is a bit different here. Now I have kind of the inner product of 2 vectors in this case. So I need to be a bit careful here of the ordering, okay? So I couldn't write here v times du transpose because that would be a matrix, okay? So one has to be a bit careful with the ordering. However, it's very mechanical. So you have a product, factor 1, factor 2. The derivative is d factor 1 times factor 2, and then factor 1 times d factor 2. So if you do it very mechanical, you will be fine. Quotient doesn't make sense here so much. I mean, we could have a component-wise quotient. We can do that too, but it requires more thinking in this case. So it's not covered with these rules. Curious is this rule, which is new. So if you have the transpose of a vector, yeah, so this is now a row vector, the differential of it is just the transpose of the differential of the column vector. Okay, so for all the trivial stuff, the rules are also super trivial. So let's find the derivative of z1 here, so x transpose x. Okay, again, let me do it on the board. This is one step more complicated here, right? So typically you would, I show you 2 ways how to derive it. So the normal way, maybe that the one that you are used to, would be that we would do the following. We would write down, okay, let me switch to the board. So first of all, phi of x. Notice the input is a vector, the output is a little Greek letter, so the output is a scalar. Okay, and you can also read it from the phi here, which is super useful. And this is just the inner product. So the usual way we would do it would be that we just sum up all these numbers here, right? So we would just say xi, all entries squared, and we sum over everything, right? And then you would say, okay, fine, now let's take the partial derivative with respect to x1 of this summation. And then you know only the term that varies, I should use a different letter here, xj. So only the I, which is equal to the j, is non-constant. So all the other terms in the sum disappear, right? So only one remains. So this will be 2 times xj. And now you have to reinterpret the whole thing. And now comes some funny notation. This is already a bit shaky, maybe. But we know what we mean by that. And we would say it's 2 times x, where we guessed kind of the right structure from this expression. We know it kind of for each single variable here. Yeah. And so kind of, okay, yeah, it makes sense. I can put all these xj into a long vector and have a scalar multiplication with 2. So it kind of makes sense to write it like this. Okay, let's derive the same thing without using indices. Okay, so let's avoid this and let's just apply now our calculus here. So I'll put the letter d in front of the phi, which is d in front of the x transpose x. I now put a little bit too many brackets here, but that should make it more clear. And now I can use this rule number 4 here on the slide, so which then gets me a dx transpose, let's be very precise here, plus x transpose dx. Okay, so far so good. Then we know there's a rule that we can drag out the transpose sign here, over there. Okay. Okay, and now, how do we get to this expression where we have a dx at the end? And then something without the dx over here. Now we need a couple of tricks and we need some thinking. Okay, so this whole thing is a scalar, right? This is just a real number or something. So I can transpose it. Nothing changes, right? Since this thing is a scalar anyway, I can also transpose it. So if I do this, I get x transpose dx plus x transpose dx, which is 2x transpose. Okay? So I get a 2x transpose. And now I can read off my derivative. Okay, and here comes the little gory details. So now is the derivative of phi, is it that one or is it the other one? Okay, that is just now convention, and I will fix it in a couple of slides. Okay, so that it's definite. Yeah, I'm not doing it now because I'm sure I can only do it with 50%. Safety to be right, to use the correct one. So there's one correct choice and one wrong choice. Okay, good. So that is the derivation for now a vector valued function. And okay, I think this is prettier, so this is easier. Let's go on with matrices. Again, let's just exchange all the little Latin letters with capital Latin letters, and we get these ones. So again, alpha and a is a constant, yeah, with respect to my output. So d alpha is equal to the zeros matrix. So this is really zeros of m comma n. Okay, it's just the same thing. I can drag out constants. I can have the summation here, okay, and I also in general have such a formula. Again, here we need to be a bit careful and think about it. So if I have a matrix multiplication, it means that the number of columns of U must be equal to the number of rows of V, and of course the same must hold on the other side. However, as I said, the shape of U is the same as the shape of the differential of U. Okay, so the number of columns of differential of U is the same as the number of columns of U, so I can left multiply it with my matrix V, right? And the same reasoning for the right-hand side term. So everything is fine. However, here we see that we cannot just change the ordering here. So for the matrices which have a product which is not commutative, okay, so here I need to be careful to really have the right ordering. Of course, since plus is commutative here, so that doesn't matter which of the two terms I do first. But it's good to be super systematic. So for the transpose, we have again the same thing, and now comes an interesting one. D of the trace of u, okay? That is the trace of d of u, okay? That might be the first non-trivial formula. However, I guess you never thought about it taking the derivative of a trace of something, so there's no knowledge in your brain already. So just store this one, okay? So why does it make sense? So in what situations can we just drag in or drag out this letter d? Kind of in a linear setting, okay? So if we have summation, kind of we can drag it in and out, or if we have a scalar, we can drag something in and out. So let's think about the trace, what kind of function it is. It's a summation of the diagonal elements. So I'm selecting some elements from my matrix and then I'm summing them out. So intuitively it makes sense. I'm not doing anything nonlinear here, okay? I'm just selecting elements and I'm summing something out. So it makes sense that it will commute with my differential here, okay, with this d, yeah? And it is like that. You can easily, typically run and make an example where you, for example, you could calculate the Jacobian of this matrix of the trace of u, right? So yeah, it gets already a bit messy since your input is a matrix, but in principle I think you could do it, that you calculate the derivative with respect to each of the entries in u, yeah, and you write it out having a big gigantic matrix, and then when you sum up the diagonal of this big gigantic matrix, you will get the right answer, okay? That's just how it is. Good, so here's another example. Find the derivative of now the product where we have this trace here, okay? And I'm not sure, do I do it here? Yeah, I'm also doing it. I show you what's happening, okay? So let me show you on the board. In principle, it should be as simple as this stuff. And I can try to write it down just by putting, I write it down again, so then you can follow. So my function now takes a capital X, and the input is a capital X as well, okay? So let's write a d in front of my function I'm interested in. So now let's plug it in. It's that one. Then again, this product rule will be dx. I'm dragging out already the transpose. Yeah, I'm already getting used to that one, times x plus x dx. And here I'm getting kind of stuck because how do I get it now to the other side? Those are matrices. However, let's check. Am I doing the right question? No, I'm not. On the slide, there was another function. So let's again look at this one. There was a trace of this matrix. Yeah? And if we check it, what we had on the board, here the output is the matrix. So I should have written it as AX. Okay? So in order to have a scalar, I actually talking about a different function, the trace of this. So that makes it easier because then I'm having the d of the trace. And as we know, the trace and the d commutes. So I have the trace of the whole expression. Great. Now we need a couple of rules, okay? So we need, for example, the trace of a plus b is the same as the trace of b plus a is the same as the trace of a plus the trace of b. So the trace is very well behaved. Everything is simple and easy. You can also drag out coefficients. If I would have an alpha here in front of the b, it would be dragged out as well. The trace is just a particular linear function, yeah, with all the niceties. So that basically means I can put the brackets slightly different and have this expression. Now this one here, if you look at it, I would like to transpose, okay? So first of all, the trace is only defined for squared matrices, right? Let's check that one. So the X has certain number of columns, this x here has certain number of columns, so the dx has the same number of columns, and then I transpose it, so this thing has as many rows as the x has columns. Okay? Yeah.
What is happening to the second transpose on the right side?
Oh, it's gone. Thank you. Yes, it's missing. That's just the typical behavior when you do the matrix differential calculus. You're feeling super powerful with these matrices, and then at the end you check your derivative. I will tell you in a minute how to check your derivative, and it's not working. And then you are looking for exactly these kind of mistakes. Thank you. However, my implementation, at least certain programming language, would have yelled at me at some point because there's a size mismatch. Yeah? But very good, so it should be there. So now, what can I do with that one? There's an interesting formula, and the interesting formula is that the trace of A times B is the same as the trace of, now I'm not want to say something wrong here. Of B times A. So I can also flip the ordering of two things here. But let's see, does it help me already? Okay, I need another one. I also need the trace of A is equal to the trace of A transpose. That's another one I need. The good thing is, these rules are actually super simple to prove. Yeah? You can look at them and make an example, and then you see that they're right. So let's look at that one. First of all, the trace is only defined for a squared matrix, and the trace looks only at the diagonal. So what is changing in A transpose are only the off-diagonal elements. They are flipped, but the diagonal stays the same. Okay, so that's the proof for that one. This one is a bit more complicated, so let's prove it for fun. Okay, so the trace of A times B. For this, you need a good way to write out this product here. Okay, let's say A, ij are the entries of that one, okay, and B, ij are the entries of K. Then I could say that this is basically the matrix of entries ik, where I'm having I times j, b, j, k, and I'm summing out the j. Okay, so now what does this notation mean? Or maybe I need some notation like this to say that I can write the matrix A by writing down all its entry, a formula with ij's of all the entries, and now suppose I'm saying, oh, I'm putting square brackets and then I'm getting back the matrix. Okay? So if I do this, then this is the entry for the product, yeah? Where, let's look at it, so the outer coordinates here are the outer coordinates of my matrix multiplication, yeah? So this is where the index I goes, this is where the index j goes, the index j goes there, and this is where the index k goes for my matrix multiplication. And then I'm doing row times column, which is like iterating with this index j along the columns of A and the rows of B simultaneously. Okay, and that's exactly what I'm doing here by summing out over the j and having the second coordinate for the A and the first one for the B. And then the outer ones, those are the ones that I'm taking out to get my new matrix. Okay, so far so good. So now how do I go on here? Now I need some tricks. Let's write out also the trace. So the trace is giving me another summation, and I'm basically summing out all the diagonal entries. So those are the entries where I is equal to k. Okay, so I'm summing out all entries over I of this inner matrix Aij, where my k is equal to I. So B times I. Okay? So basically now I'm saying the trace is summing out the diagonal, which is the other locations where I is equal to k. So let's remove k and plug in an I. So I plug in an I over here. So I get this expression. Next, I'm exchanging the summations. Flip that one. Then I'm exchanging those ones, since those are scalars. And now I'm doing the same procedure backwards. And then the outer summation becomes a trace, and the inner one becomes a summation over the entries. Okay, so basically this statement here, this one, is saying I have an inner summation for the matrix-matrix multiplication, I have an outer summation from the trace, and if I exchange them, I get exactly the trace of the B times A. Okay? So under the B times A, you can rotate your matrices. You could also do something like the trace of A, B, C is equal to the trace of C times A, B. So I'm kind of rotating the C to the first side. How can I do it? I'm just applying this formula. And I'm saying now my first matrix here is Z1 and my second one is Z1. Okay? And they stay in order, but the first one is going to the front. So under the trace, you can arbitrarily rotate your matrices. Good. So this kind of proofs are the ones that you do to trust your formulas, or you just trust the formulas. Okay? Good. So far, so good. Now we have enough material. I think this is all we need here. So I guess we can just say, I just put a transpose sign here, in here. So I'm using this formula. So the trace of A is equal to the trace of A transpose. Okay, let's use that one. I'm just putting another transpose sign in here, and then I'm getting the trace of X transposed dx. Okay, so that's what I'm getting from that one. I have it already here, so I'm having it twice. Now, I'm having a nice expression here where the dx is on the right-hand side. However, it's inside the brackets. So now it goes on with the roots of the matrix differential calculus. If you have such a function where the output is scalar, the input is a matrix, your goal is a formula like this. So your goal is a formula like trace of something, which is your derivative actually at the end, times dx. And then you can read off magically the derivative of it. Okay, so the derivative here will be, I think, x. Now again, I'm mixing up with the trace or not, so maybe with or without. Anyway, so that is the derivative, 2 times. Good, so this end step is a bit shaky, but let's get to that one. Okay, so that is the derivation. Okay, it's even slightly different. I first show you this table here now. So this is the identification table. Now, if you have a function, now you need to understand, do you have scalar, vector, or matrix valued output, and do you have scalar, matrix, or vector valued input? And for each of these 3 by 3 possibility, you will find one row in here. Okay? So it's just very verbose, this table. So let's look at it. So the simplest one is phi of x, which is scalar input, scalar output. Here you need to derive this equation. So the d phi must be equal to some expression of xi times d xi, where in the alpha of xi there is no d xi anymore. So the d xi must be isolated to the very right-hand side. And then you can read off the derivative here. And at the end, the shape of the derivative will be 1 by 1. Okay? Let's take the next one, vector valued input. In this case, we need to get this form. We need to find an expression that is an inner product of some function of x transpose times dx. And then we would say the derivative is this function transposed. Okay? And then the shape of the derivative is 1 by n. Okay? Since the input might be an n-dimensional vector, then the derivative in this case, by this convention, it's a 1 by n. Now comes the interesting one. Suppose we have a vector, a matrix valued input, then you need to bring it to this form here, the trace of the matrix times dx. Now, where does the trace come from? How is it like a special case of the line above? So let's look at the line above. The line above is multiplying an n-dimensional vector, taking the inner product with another n-dimensional vector, which basically means summing up all entries, of the first entry of ax times the first entry of my differential, the second entry of my ax times the second entry of my differential, and summing all of these up. So what would be a generalization for matrices? Basically, taking each entry of this matrix A of x and multiplying it with each entry of my matrix dx. Okay? and summing everything up. So let's see that this is exactly doing it. So let's try to write it down. So basically what I'm saying is the trace of A times B, let's say A transpose times B, yeah? So that is exactly the summation of ij of all the entries iaj, bij. Okay, no brackets here. So these are the products of each entries, and we're summing them all up. Okay? However, this is exactly what we computed over there. Yeah? So how is it exactly that one? So the summation over ij is exactly this summation here. Yeah? Then we have here the entries ij, and here we have ji. So it's slightly wrong. However, check. Here we have a transpose sign. Here we didn't. So if I would put a transpose sign, for example, over there, basically these two entries would be flipped, and we see that the trace of the product of A transpose times B is just the sum of the all entries where we multiply them with each other. And this is very much like the inner product, right? If I have a vector A times B, it's the summation over all I of IA BI. Okay? And this is a natural generalization for matrices. It looks complicated with the trace and the way to write it, but this is just a way to write the inner product for those ones. Actually, there's the Frobenius norm that you might have heard already. So the Frobenius norm of a vector would be, I'm not sure how to write it, maybe Frobenius squared, I'm not sure, but this is exactly A times A. Okay, and that is exactly all entries squared, summing up all entries squared. Now, using this trick, we can also write down the Frobenius norm for a matrix, which is just the trace of A transpose A. This is the generalization of the inner product for matrices. Okay, and that is the summation over ij of all entries squared. Okay, and for completeness, let's have the alpha squared Frobenius one as well, which is just alpha squared. Okay, so this is generalizing the same idea from scalars to vectors to matrices. Why does it get so messy? Why does it get so complicated? Because we have a two-dimensional way of writing down here these matrices, right? That's the reason. This formula at the end kind of is the simple one. Also the one which we could generalize, right? So suppose now we have some tensor, not a matrix, but a cube of numbers or a hypercube of numbers. Then we are out of notation for this intermediate step, but we could say, okay, it's a summation of I, j, and k of this weird letter of all the entries squared. Okay? So that's like something very natural. So in a way, we are calculating here in this complicated formula trace of ax times dx, we are calculating the inner product between two matrices. Okay? So far, so good. Now, here's another one. So what about that one now? Why vectorized A of x? First of all, what is this vec operator? Okay? The vec operator is exactly that what you would expect it is. It's vectorizing a matrix. So suppose I have a matrix A, which has these entries, A, let's say M1, Mn. So those are all the entries. Then the vec of a matrix A is just a long list of all entries, where again, I think I can mess it up. There's a 50-50 chance that I did not mess up at the end. The question is whether we do it by columns or whether we do it by rows. And the rest must be compatible. All the other operations must be okay. So that is the vectorization. Interesting. This gives us another way to write this thing up here, right? We could also say, okay, that is the vectorized version of A transpose with the vectorized version of B, right? This is just also multiplying all entries with each other and summing everything up. Okay? And similarly also down for this one, I could also use this vectorized notation. So this is just a way to trying to write things up. So why do I vectorize my derivative here? Because I want to have the shape of the derivative to have the following form. I want to have the number of input dimensions, I want to have them on the right-hand side, and the number of output dimensions later I want to have them on the left-hand side of these dimensions. Okay? So that is important for the following reason. So when you calculate the Jacobian matrix, you typically have a vectorized valued function that takes vectors as inputs. So it's kind of natural in the Jacobian matrix to have as many columns as input and as many rows as outputs. Okay? However, if your input is a matrix, then it's kind of getting unclear, right? I mean, in principle, you want to have as many columns as there are entries in your input. And if your input is a matrix, you want to have n times q many entries or n times q many columns. Similarly, if your output is a matrix, you want to have in your Jacobian basically as many rows as there are outputs. And then the whole thing gets messy. But it's not getting better if you would use these partial notation. So that also wouldn't make us more happy. So let's look at it for a second. So suppose now I think there's notation, I'm not super sure, but there's this notation of the gradient, right? So you can have the gradient of a function, and let's say it's a vector valued function, so you use a small Latin letter for this, of a vector x, yeah? Something like this, and that is basically the matrix where I'm having the partial derivatives with respect to the xi. Now, this is something I always mess up, but it's something like this. So basically, since this is a vector, I can take the j's entry, and I can have the i's entry of my input, and I can form this matrix. That is typically the gradient in general, okay? Is it right? Maybe the gradient is typically defined for a scalar valued function. I'm not super sure. Yeah, maybe. But if we would, then it's just has the same shape as the x. However, if I have a multidimensional output, then it kind of gets more complicated. Now suppose I'm also having a matrix valued output, then in principle now I want to have as many rows as there are entries in A. Okay? So I always want to, my derivative should tell me, no matter what the weird shapes are here, for example for this one, matrix valued output, matrix valued input, in that case I want to have the columns of my derivative to refer to the input dimensions and the rows of my shape of my derivative to the output dimensions. Okay? That's why it's chosen like that. It's kind of arbitrary but consistent, okay, in a clever way. Good. So let's check out the other ones. So those are the most important ones, because those are the ones that refer to loss functions, where we have a single digit that we want to minimize in an optimization method. Those are ones which we can also do because we have a good notation, but which are not happening so often, right, in the world. So how do they look? We could have something like this. The A of xi is a vector times a scalar differential. Then the differential is just this A of xi. Okay? That's just the right choice. And so on and so forth. The most complicated one is this one here, where you have a matrix valued function of a matrix input. So you get a matrix, and you multiply the vectorized version of this one with that one, okay? And then the A of x will have the right shape at the end, ideally. However, typically we are in this area up here, in the first three things. Example linear regression, yeah, you want to maximize the log likelihood or minimize the negative log likelihood. So the negative log likelihood is a scalar, and your input is a vector. So you're in the second row in this case, and you need to bring it to such a form of an inner product. Good. I think I skipped one slide. So this is a summary of the rules we've seen so far. So those are the rules that I've showed you already. Yeah? And these are further rules. Let's look at them. So if we have the vectorization operator of a matrix, it's just a vectorization of the differential. Okay? So this is something The vectorization is just a reshape, right? When you do a reshape with a matrix. And the reshape is again some super simple linear transformation which behaves well with the differential. Here's the one with the trace. Now comes the one with the Kronecker product. So you might not know the Kronecker product. It's like a I tell you what it is. It's a multiplication you always want to avoid to execute, right? Because it lets your memory explode. So suppose you have two matrices of any shape. Okay, so let's say the A is in R to the whatever, let's say for concreteness 10 times 17. Okay, so that is the wet. Let's take my own one. 10 times 17, and I have another matrix of another shape. Let's say 5 times 3. Then the Kronecker product is the following matrix. Again, here are two possibilities, and I'm writing down possibly the wrong ones, but you will see what I'm talking about. So it will be the entry A11 multiplied by the full matrix B. So this is filling up a whole corner, yeah, of size 5 by 3. Then the next entry, matrix valued entry, is A12 times B. So this is filling up another 3 columns, and so on and so forth, up to A, which one is it? It's 10, 17 times B. So this is filling up the last corner here, okay? And here you also see the two possibilities of defining the tensor product. I could have switched the roles of A and B, and I get a slightly different matrix, which looks different. So this is a matrix which lives in the space of 10 times 5 times 17 times 3. Okay, so it's really getting large. So if you have a big data matrix and you do this operation, you are you're filling up your space very, very quickly. You never do this practically. However, sometimes in your math derivations, in between you get a Kronecker product, and then you need to get rid of it again. Okay, and then everything is fine. Good. Let's look at the formula. So Kronecker product is just a complicated multiplication. Right? Why do I have so many possibilities for multiplication with matrices? Yeah, I can do it component-wise, I can do this matrix-matrix style, I can do this Kronecker style. At the end, it's just multiplying elements from one matrix with elements, particular elements from the other matrix. So it's just multiplication. So the rule is exactly the same, yeah, as we have for multiplication. Now everything is a Kronecker product. What about that one? That is the Hadamard product. So this is the one where I'm doing a component-wise multiplication. So, and that definition fits down here. Yeah? So basically the A times B is the same as numpy A star B. So basically every component in A gets multiplied with its matching component in B. So the shape must agree. Okay, and the size does not increase. So that is the so-called Hadamard product. Okay, so the usual product, by the way, as you know, is in numpy. It's A, and then you have this letter A. So this one. Okay, and I guess now for the cron one, I guess there's also one. It must be something like NP cron. Yeah, you can play around with. I think it exists, this function cron. Something like that. You never use it, yeah, because it explodes your memory. Good, for the Hadamard one, it's also just selecting columns and entries, and then you multiply some things. So the formula is again exactly the same, but now using Hadamard. Next one, so this is the one that you might have seen already in your derivative classes, right? So this is a scalar to the power of another scalar, and that is just alpha times phi to the alpha minus 1. So that is just the usual formula that you are used to. Okay, that is, I think, one that you learn in class. So I think you learn the summation, the product, the quotient, and you learn then, or you can then derive this one down here, maybe yourself. So what else do we have? Now this is a fancy one, the differential of an inverse matrix. So why is that a fancy one? Because here you cannot just use derivative of the sub-indices and trying to be clever about it at the end to read off some matrix expression. If you have the sub-indices and I take the derivative of u11, yeah, I'm getting nowhere, right? Because I don't have a closed form expression for the inverse kind of. The inverse is the closed form expression. However, in the differential calculus, you can. So now the answer here is that the differential of the inverse matrix is minus the inverse matrix times the differential of the U times another inverse matrix. And it's surprising, right, that the formula looks like it. I can give you a very quick proof of that one, that this is really true in a second. But let me first show you what does it buy you. So here you have an inverse matrix, the differential of an inverse matrix, and here you have the differential of the normal matrix. So you kind of move the differential, so you kind of move the inverse out of the differential. So basically the expression inside the differential got simpler, yeah, but because you removed the inverse. However, you had to pay for that one by now multiplying from the left and from the right with the inverse matrix. So now how do you prove such a formula? Let's see whether I can invent it. Basically it follows from the product rule. So that is not such a big surprise because the inverse matrix is something about product, right? So the inverse, maybe I should switch. Oh, I did already. Okay, hopefully I showed you the other thing. So basically the inverse is defined like that, right? U times U inverse is identity matrix. Okay, let's calculate the differential of this expression. Then we get I is the constant, so it's 0, and it's a 0 m times m matrix. And for the other side, I'm using the formula for the product, so it's du times u inverse plus u times d u inverse. Okay, great. So now I can bring this one to the other side. So I'm getting over here a minus du yeah, and I'm still having that one, but now I'm multiplying from the left also with a u. And then I'm having the formula. Okay? So I'm just applying the product rule to this equation and shuffling around a bit, and I have the formula. So now this is kind of powerful because, as I said, the inverse kind of needs to look at all entries simultaneously, right? So it's not easy to take the derivative of the 3/4 entry and then just cleverly combine everything at the end. Surprisingly, we need twice the inversion at the end for the derivative. So that's quite a nice rule here. Here's another one, logarithm of, not logarithm, let's take the logarithm first. So logarithm of the determinant, that's also a fun thing. So the determinant is, as you know, the product of the eigenvalues, right? Maybe that's not how he learned it, but it's like a nice property. So the determinant is the product of the eigenvalues. So product and logarithms go together very well because logarithm and product kind of commute, and a logarithm turns a product into a summation, okay? That's exactly what's happening here, right? So the logarithm takes the product of the determinant and makes it a summation, where the summation is now denoted by the trace. The trace is the summation of the diagonal entries. And then inverse matrix times du. I have no good explanation why this formula turns out to be the right answer. But this is then the answer here. By the way, the determinant is a scalar, the logarithm of it is a scalar, so it kind of makes sense to have some operation that is giving us a scalar, which is the trace, okay? More complicated is the differential of the determinant itself. It's a more complicated formula. It's the same one as that one, but we need additionally to multiply it with the determinant of u, okay, for whatever reasons. In the Magnus Neudecker book, there are like derivations of all these formulas. We don't have to worry about it. What else do we have? We have the exponential function of a scalar, which is just as you would expect it now when you get used to this. Then we have the trace of the differential of the matrix exponential. So that is the matrix exponential function. That is something that physicists sometimes have, right? Sometimes use. So that is the exponential function can be generalized to matrices as well. And that one also has a certain differential, which is derived in here. Okay? Good, so far so good. So those are some tricks. However, there are many more tricks, so here are more tricks. I just write them down for you. Those are the tricks I'm usually using when I'm calculating derivatives. So, as I said, the trace of A times B is the trace of B times A. So that was a simple one. And then there are some weird ways of rewriting stuff. One thing, for example, simple is vectorizing a vector is the same as vectorizing the row vector is exactly the same as A. So far, so good. The trace of an inner product is the same as the inner product, and so on and so forth. This is one also fun one. The determinant of a matrix exponential is the same as the exponential function of the trace of A. That's another fancy one, which is, I think you don't learn in linear algebra. And here are many, many more. Most of them kind of trying to be clever in implementing something. So what about this one? Let's look at that one. So the trace of A can be written in a complicated manner that is sometimes useful. So let's first look at that one. This notation, diag of A, is the diagonal of A as a column vector. Again, notice there's also here another diag which has a capital letter in front of it. So the one with the small letter in front of it takes a matrix and gives you the vector along the diagonal, and since it's a vector, it has a small letter d in front. This diag of a vector is giving you a diagonal matrix. So there are these two functions, and from the capital D or small letter d, you know whether you have a vector or matrix. So basically extracting the diagonal of a matrix and multiplying it with the one vector from the left-hand side is summing up all entries. So that is just the inner product with one vector. And now the diagonal thing can be also written as the Hadamard product with that one. So that is something you can figure out yourself very simply. Basically, Hadamard product with an identity matrix here basically sets all off-diagonal elements to 0. Okay, that's what's happening here. And when you multiply it with the one vector, it's like selecting all the diagonal elements. So when you try it, it will work out. This is another fancy one, which sometimes is super useful because some formula might give you an expression like that one where you have a DC here, so here you have a differential, and you want to isolate it, then there are ways to isolate that. And so on and so forth. So now, for an exercise or for an exam question, do I need to memorize all these formulas? Of course, right? Of course not. So, yeah, so you don't have to memorize them, right? I also don't memorize them. That's why we have books and paper, or maybe also PDF files, right, where we can look them up. It's just here so that you know they are there, and if you have a complicated derivative, you know, oh, there were all these tricks. Let's try them, okay? Good, so far so good. Suppose we derive the derivative now. How can we check it? There's a method of finite differencing. That's now basically the 101 differential formula, how the differential was defined. So let me write it down. How did we define in school basically? Yeah, question. Sorry. Great. So the derivative of a function like that one. So how was it defined? It was defined to be the limit epsilon against 0, right? And then it's just the difference of phi of xi plus epsilon minus phi of xi divided by epsilon. Okay? So where we now see that the epsilon is kind of, like in dx, it's like a little change of the x. Yeah, it's like having a thing in here. We can also have a slightly different version of this one where we kind of add a little epsilon and we subtract it, and then we are going kind of simultaneously from both sides, but then we need to divide by 2 times epsilon. Now, if I omit this limit here, then I basically have a formula that I can calculate in my computer to calculate the derivative, right? I can just take a small epsilon, like 10 to the minus 5, add it to my input and subtract it, and calculate the difference divided by 2 times epsilon. Let's look at the code. So that is exactly what we are doing. No, only that now here this epsilon is called a little delta, okay? And at the end we divide by 2 times delta. So that is the 2 times epsilon from the board. And my grad f, what is it? Basically it's something where I'm calculating the difference of my function value plus a little distortion minus my function value minus a little distortion, okay? And now what about the other stuff around here? So that's just a clever way to write a finite differencing method that works with any tensor of any dimension. So let's think about it. So I need to have this offset for my input. So the input must be some matrix of the same shape as the x. That's this NP zeros like x. So that's a matrix that contains only zeros. And then I'm iterating over all entries of this matrix, and I'm setting one of the values to delta. Yeah? Then I do the computation, and then I'm setting the same entry again to 0. Okay? So this is taking a big zero matrix, putting one entry to delta or to epsilon, calculating my function, calculating the difference, and then setting it back to 0 and putting the next value and setting it to delta. Okay? So it's just iterating over all entries. And the way I implemented it here was in such a way so that the x could be a 3 times 5 times 7 times 8 matrix, and the code will work and do just the right thing. Okay? It could be just also a scalar, or it could be just a matrix or a vector. That's also working. Question?
Why should you always check your derivatives?
Oh, because these stupid transpose mistakes. And I show you some examples. And in the slides, there are some more examples that I worked out. And actually now I decided to have always code in my lecture, right, as you know. So I wanted to have a little Jupyter notebook for this example. And by doing that, I found lots of mistakes on my slides. Okay, so they were just wrong. So just by checking them with finite differencing. The thing is, this recipe is super simple to understand, right? I mean, this you can verify by looking at it. You can verify that the code is doing the right thing, right? The code is so simple so that you can be sure this is doing the right calculation. These complicated formulas that you derive, you cannot check so easy. That's why this finite differencing method is a nice way to check your derivation that you made by hand. Okay, here's another implementation using MATLAB. Basically using the same tricks. Also, MATLAB, I don't know whether anyone is still using it. I was using it in 2012 and also many years before. And so I have this implementation for that one in MATLAB as well. But this is now my modern version in NumPy, which does the same thing. So the general recipe, again, you put the letter D in front of it, then you need to identify constants and variables, then you do the transformations with all these weird rules that I showed you and some good intuition. The idea is always bring it to the form such that from the identification table you can read off the derivative. So that's it. So pros and cons of this method. So it's a very clean notation with few sub-indices. Okay, so that's good. It is really super powerful. So in this book, Magnus and Neudecker, they also even show you how to calculate derivatives of eigenvalues, which I find really fancy. So you have a matrix, and you could imagine there is an eigenvalue operator, which gives you the eigenvector of the largest eigenvalue. How do you calculate the derivative of that one? So that is really super tough, right? But with this calculus, you can do it. Some formulas get really complicated. You always need to check the shapes of it, and it requires quite a bit of practice sometimes and a few tricks. However, when you have a problem like that in your science project or in your PhD thesis or in your company or something, and there's a complicated problem that you can solve by deriving a derivative, yeah, you will be the Superman or the Superwoman who can do it with it. And it might take you a week until you figured out all the tricks, but typically it leads to a solution, okay? By the way, intuitively, if you have a little function that computes something and you want to have the derivative of it, now we use PyTorch, but maybe it doesn't apply to PyTorch. Typically, the implementation of the derivative has a similar complexity, which I find, it's just an observation, so I cannot prove it, but it looks like it is. Examples. So, find the derivative of this least square problem, okay? So here's the derivation. You put the D in front of it, and then you plug in everything, so you need to make sure, so what does it mean, this squared here? What exactly does it mean? It basically means I have a vector, and when I square it here, my notation says I taking the inner product with itself. Okay, so that is now the interpretation of these sloppily writing it down like that. It could mean anything. It could also mean squaring all entries, right? If you do it in Python, then you would write **2, on a vector, it would square every entry. That's typically not what's meant by least square. By least square, it's meant that you sum up all entries. So it's the inner product of this vector with itself. Also, you see as a redundancy in the notation, we use the scalar as the function name. Okay, good. When you do now the math, basically you can do some tricks here, basically applying the rules of the calculus, and you get this expression, some new vector transpose times a times dx. And then you can read off the derivative, where here now I transpose the whole thing. So why did I transpose it? Because that's how we wrote down the... okay, I didn't write it down like this. Okay, I transposed it. I messed up here. So it's either transposed or not, okay? But at the end, it doesn't matter so much, okay? Just you need to be aware that there are often two answers to that one. So it's not consistent with the rest of the stuff that I wrote down. So this should have been the transposed of it, okay? Good. And maybe why did I do it like this? Because, okay, it's a scalar function. Actually, I'm interested in the gradient, and the gradient has the same shape as the x. Yeah, for gradient descent, I later on want to say x plus learning rate times my gradient, and when the gradient has the same shape as x, I can just sum them up and everything is fine. And this thing now has the same shape as x. Okay, that's why I wrote it here. However, it's not consistent with this stuff with the gigantic Jacobians, where the number of columns should be the number of input and the number of rows should be the number of outputs. Here's another one, and that might be more fancy. Suppose you have this expression here. I mean, it comes from this linear regression one, but now I want to calculate the derivative of this function with respect to x, okay? This is already something I think you cannot do without the calculus, okay? And when you do the derivation, it gets more and more messy. So here are all the details, and I hope it's true, but how does it work? I put the d in front of the expression, and then I'm using the product rule, right? So I'm applying the d to the first one, and I'm applying the d to the second one, and so on and so forth. And using the rule for the inverse, I'm giving this x transpose x inverse a name a, kind of to make things simpler. And then at the end, I'm getting this super gigantic expression, and it's a big mess. And then I should look back at my initial problem. Do I really need the derivative of this function, right? Isn't it maybe only a sub-expression of what I really want to calculate? Because typically, I'm not interested in a vector-valued function, right? I'm interested in loss functions, which are scalar. So this is the true answer, but it's horrible, right? It's looking so complicated. Often, we are looking at scalar functions. So let's make it a scalar function by multiplying it with a vector from the left-hand side. Now it's a scalar, right? The output of that one is a vector times some constant vector from the other side, okay? And now if you do the derivation, everything gets simple, but be aware of the transpose signs and be aware of the ordering of terms, yeah? And then you get like a nice expression without any Kronecker products, okay? And then you can read off the derivatives like before. You might not think this is a nice expression, but this is a complicated function, right? By the way, where does it appear? Is it important? Suppose the X is a convolution matrix, right? And a convolution matrix is a matrix which takes as an input a vector and then does some Fourier transforms to it and some other things and some inverse Fourier transforms, and to generate like the Fourier transformation matrix. Yeah, but you want to optimize with respect to the filter, to the input to the Fourier thing. And you will later on use it in such a formula because you are doing some fancy stuff with it. Then you want to calculate the derivative of this whole expression with respect to the filter of this matrix X. And then you need this, okay? Then you really need it. But you are not done yet at this point. But then you would have to go on and plug in the expression for the X. Where would you do it? Okay, suppose the X itself has a complicated expression. You do this derivation, and then you need to plug in for the dx now the rest of the expression and further isolate the d to the end, okay? I will show you code for that one too. Maybe I should show you right away. So let me show you the code. Okay, so this is now about checking the derivative. So here's finite differencing with NumPy. That's the first version. And on a later page, I show you also how to do finite differencing with, how to check derivatives with PyTorch. Okay, you can also do that one. It's also in the notebook. This is the implementation from the slide. So this is the first example that we've seen. This is an implementation of the least square example, where my phi, I call it phi1, is basically y minus a times x transpose times y minus a times x. So this is just the least squares formula. Then I did some work on a sheet of paper and derived by hand this derivative, and I want to check that one. So I want to check this grad phi of 1. So I take a random input here, I calculate the gradient with respect to my derived formula, and I use the finite differencing, and I plot them both and even calculate the norm of the difference. And as it turns out, I get the same answer. Okay? It's not exactly the same answer, but approximately one. So let's more look at this horror function here. So this is the one, C transpose times, and then comes the inverse of x transpose x times x transpose times y. Okay, and for that one, we derived this complicated looking formula. And of course, I can do the same check. The finite differencing doesn't care whether my input here is a matrix or a vector, right? Since it's creating locally a dx of the same shape and then putting ones at every location, or epsilon. And as it turns out, so now here this gradient is also a matrix shape. I put it in matrix shape, and I get the same numbers. Okay? And now why not always use finite differencing if I'm so sure? The runtime of this one is super fast, and the finite differencing needs to iterate over all elements. So if I have a 10 by 10 matrix for x, then basically the runtime will be also 10 by 10, but calling the function itself. So this function phi2 will be called as often as there are entries in x. This function does it just with one call, which is approximately a constant time as expensive as the phi2 function. Yeah? So the derived formula is much more efficient than the finite differencing one. Okay, so here's another example, the Rayleigh coefficient. So let's look at that one. So I show you that one later. So here's another one. So the Rayleigh coefficient, this is a function which is, I think, it's the largest eigenvalue or something. It's computing the largest eigenvalue if you let x go somewhere or something like that. Yeah, I think you need to let x optimize over x or something. Yeah, I think, you maximize the Rayleigh coefficient, this one, so you maximize it with respect to x, and this gives you the eigenvector of the largest eigenvalue. Okay, so that is what the Rayleigh coefficient is doing. So let's calculate the derivative of this one for x. And again, it looks a bit horrible, but it is just applying the product rule and all the other rules. Again, let's look at it. You apply these rules, and then you have this dx in here, and it can happen to be at many locations. So you need to shuffle around a bit the terms in such a way to isolate it to the very end. Okay? And then you get the derivative of this thing with respect to the vector x, and you can read it off, and you can implement it as well. So this is an implementation. So this again is my function phi3, x transpose times a times x divided by this one, and this is my derived formula here, and I can compare it basically with the finite differencing solution. Okay, so far so nice. As you know, PyTorch is a toolbox for neural networks, and or with other words for deep learning, or with other words for differentiable computer programs. So PyTorch can automatically differentiate your computer programs to calculate gradients. Let's try to use it here as well to check gradients. So for this, I need to have an implementation that takes a function f and something, some tensor x, and calculates the derivative of it at location x. And that can be done in Torch very simply. So you just call your function once. So you do a forward propagation, yeah, putting in a vector at the beginning, run it through the neural network. We will talk about neural networks later. But you can also view it, you put an input into your program, you calculate the output, and then you do backpropagation, which is just y.backboard in PyTorch. backpropagation, and then you can read off the gradient, okay? So if all functions that you are using, if all operations are implemented in PyTorch, you can use it to calculate also super efficiently gradients, okay? So here comes again the least square problem, and here I'm comparing the output of my implementation and the gradient that I receive from PyTorch, okay? So that's a nice thing. However, in the implementation here now you need to be a bit careful. I now need to use like the torch rand n function. For the variable x, I need the torch rand n function, and I need to tell it requires the gradient. So there are some things that you need to adjust. So similarly here, up here in my finite differencing, I try to minimize the influence of NumPy on this implementation. However, at some point here you needed it. And this is incompatible with the torch version. So they are like two different linear algebra worlds. Anyway, so you can also do the same examples now with torch, and they are just for your pleasure implemented in here. Good, so far so good. Let's go back to the slides. I'm almost through. So here's another fancy one. Suppose you have a gradient descent method, yeah? So you're doing steepest descent. You're having some update rule like this, yeah, where you have an estimate already for your x, and now you are using some steepest descent for the least square problem, okay? You have an optimization algorithm. You iterate it. Around this xk plus 1 is the for loop, okay? So you do it several times. Suppose now I want to calculate the derivative of the output of my steepest descent method with respect to the initialization, x0. That's quite fancy. That's super hard to do by hand, but with matrix differential calculus you can do it, okay? You can also calculate the derivative with respect to the learning rate, which is fun, yeah? So why not do a gradient descent on the learning rate of some algorithm? Yeah, you can do this. You can also calculate the derivative with respect of your matrix A, okay? And this is just giving you the solutions here. This is not the derivation. The derivation is quite painful, and but it's all in this bn142.pdf in the public folder. Good, I'm almost there. The last thing is I wanted to just very briefly show you, so are indices now so evil, or are they, so should we avoid them at all costs? No, be always aware that there are always the passage of using indices. Sometimes it's nicer. So I'm calculating the differential of the trace of A times the diagonal matrix with V along the diagonal. And if you do it without indices, you can do it, but you need some of the super tricks from the slides before. If you do it slightly different, like this, and you just rewrite this trace of A times diagonal of V in a clever way, the derivative gets much easier, okay? So you shouldn't be dogmatic about not using indices, but there are situations where you will get stuck with indices and where this differential calculus will give you a solution. Okay, that's it for today. I hope you enjoyed it a little bit. Yeah, it is super useful, and there will be an exercise about it. And when you need it, you will be happy that you learned about it. Okay? Okay, thanks for your attention. I see you on Wednesday.